Hello, today we're going to have a look at forming halogenoalkanes via free radical substitution mechanisms. In this reaction, alkanes such as methane react with a halogen, represented here by X, to give us our halogenoalkane and HX. Now specifically, that could be methane reacting with chlorine to give us chloromethane and HCl, or in a similar way, methane will react with bromine to give us bromomethane and HBr. This reaction occurs via a mechanism. Now the first stage is initiation. Now the essential condition that's needed for initiation is either ultraviolet light, which can be provided via sunlight, or a high temperature. Now, in a initiation stage, free radicals are being formed. But what are free radicals? Well, they're a species that have an unpaired electron, and this makes them highly reactive. If we take a bromine molecule, for example, this has a covalent bond represented by the line between the bromine atoms. Another way of viewing this covalent bond, rather than simply as a line, is as a shared pair of electrons. Now, in the initiation stage, homolytic fission occurs of this covalent bond. Now, what that means is that the bond is broken with one of the electrons going to each of the bromine atoms, forming two bromine radicals. And we represent the bromine radical by writing the symbol Br with a dot. However, in the exam, we don't need to be able to describe homolytic fission in that detail. We simply need to be able to write an equation showing a homolytic fission step or an initiation step as it's otherwise known. So for example, we could write bromine forming two bromine radicals, or similarly, chlorine would form two chlorine radicals. When we have a simple radical such as bromine or chlorine, where there's only one atom involved, we are allowed to put the dot anywhere on the atom, but quite often you'll see it written after the atom or in the top right hand corner. The next stage in the mechanism is called propagation, and this involves two steps. Propagation is probably the most confusing and least well understood of the stages in free radical substitution. In the first step, our alkane reacts with our halogen radical that was produced in the initiation step. This produces a molecule of HBr. This is done by the bromine removing a hydrogen atom from the methane molecule. This leaves a methyl radical. Now the methyl radical is now a more complex radical, and it is important that we put the radical dot, which represents the unpaired electron, on the carbon atom. It must not go after the CH3, but it must be shown on the carbon. The usual way of writing it is as is shown here, with a dot before the carbon, but it is sometimes represented either in the top left hand corner or above the carbon atom. But as I said, it is essential to get the mark in the exam that radical dot is shown on the right or correct atom in the complex radical. In the second propagation step, our methyl radical from step 1 reacts with a molecule of bromine. Now in this case, that takes one of the bromine atoms to form bromomethane, our product, or one of our products, and it forms or reforms a bromine radical. Now the common error in this step is that people think about bromomethane as being the product of this reaction, and so they want to try and form it in the first propagation step. There are of course two products in this reaction, HBr and the bromomethane. Now it may be we think about this reaction as a way of making bromomethane, but it is actually formed in step 2 of propagation, not in step 1. And that is where most people get confused. In step 1, the bromine radical is taking a hydrogen off the methane. That forms a methyl radical, which is then able to take a bromine atom from a bromine molecule, forming our bromomethane and reforming our bromine radical. Now we mentioned that this is called a chain reaction. The reason it's called a chain reaction is that the bromine radical that's formed can then attack another methane and form another bromomethane, which also forms another bromine radical, which can then attack another methane, and so on. So the initiation only needs to happen at the start. Once those radicals are made, this reaction can carry on going through the propagation steps. In the same way that it is possible for two free radicals to be formed by homolytic fission of a covalent bond, the reverse process is also possible. So two free radicals can come together and reform a covalent bond. Now in the reaction mixture we've got bromine free radicals, and if two bromine free radicals came together they would form a molecule of bromine. But we also have methyl free radicals, and it is possible for a bromine radical and a methyl radical to combine to form bromomethane. And of course it is also possible for two methyl radicals to combine, in which case a molecule of ethane is made. So in this reaction a small amount of ethane will be produced by this termination step. Now this reaction is not a particularly good way of making haloalkanes. The reason for this is twofold. Our haloalkane will undergo further substitution. So that is, it will react with another halogen molecule to produce a di-substituted haloalkane and of course another molecule of HX. But the reaction will not stop there. Our di-substituted haloalkane will react with another molecule of a halogen. Again, another HX is formed, but this time the tri-substituted haloalkane is formed as well. This will continue until all of the hydrogen atoms on our haloalkane are replaced by halogens, or the halogen runs out. So the proportion of the different products can be influenced by the ratio of the alkane to the halogen at the start of a reaction. The less halogen you have present, the less substitution to products will be formed in the majority. If you use a large amount or an excess of the halogen, then you will form more of the more substituted or even the fully substituted haloalkanes. Another problem of this reaction occurs when longer chains are used. If we have an alkane such as propane, we could form a product such as 1-chloropropane. However, there's no selectivity about where the halogen will attach onto the carbon chain. So in this reaction, we would also form 2-chloropropane. Given that this would occur along with further substitution, we are going to end up with a large number of products which would need to be separated to get our desired product. So there are better ways of making haloalkanes than by free radical substitution.